Okay, Hawk, you're ready. One, and two.
Okay, so we'll start again. Does anyone have any questions before we continue? Okay, who wants to answer this question? Who can describe the is kind of relationship in their own words? Can anybody do that? And maybe with an example? Is that too difficult a question? You told me your name already. Emily?
So it's kind of A shares all the responsibilities of B, and only those responsibilities of B, just like a small section of them.
And can you think of an example of the is kind of relationship?
So if you had like a generic bar of soap, and then you could have like the soap.
That's right, that's correct. Very good, Emily, very good, very courageous. The example she gave was soap. You could imagine palm olive, is that like, that's not a very good example, but palm olive is a kind of soap. So you have to be able to say it out loud, and that sentence has to make sense in natural language. It's so funny how confusing, this is a simple concept actually. It's simple. I'm not making it artificially difficult, but I've had students say the strangest sentences in the middle of a class, in the middle of a lecture before, and the sentences. If you say the sentence out loud, it has to make sense in the natural language. So if I said something like, "A napkin is a kind of table." No, that sentence doesn't make any sense. Or a leg is a kind of table. No, that sentence doesn't make sense. It has to make sense. A desk is a kind of table. Okay, yep, I can understand that sentence. So let's continue where we left off. The drawing editor example. Here's an example of a class hierarchy, the is kind of relationship. And watch, I can do it here too. Text element is a kind of drawing element. Line element is a kind of drawing element, and so on. So we've introduced an abstract class for all of these child classes. Line, ellipse, and but. We notice that it's not optimal, right? Like lines and ellipses and rectangles are all composed of edges, generally speaking. But text is somehow different, isn't it? And groups are somehow different. It's not the same. There's something different, right? Line, ellipse, and rectangle all have this attribute representing line style. Right, a shared responsibility, but not text and group. So it can't be assigned to drawing elements, right? This line style that we want to think about, which is a new responsibility. So we can create a new abstract class to support the line style responsibility, right? You have solid lines, you have dashed lines, you have stippled lines, colored lines, right? That might not be attributes of text elements or group elements. So here we revise the hierarchy. We have now drawing element. Linear element has this line style responsibility in it, like get line style and set line style, right? And then text element and group element are off on their own. And if we look at line element, ellipse element, and rectangle element, well, ellipse and rectangle have something in common because they both have areas. A line doesn't have an area. It has a length, but it doesn't really have an area. So we might want to add that responsibility into an abstract class as well. Ellipse and rectangle share a fill style attribute that is not shared by lines, right? If you have an ellipse or a rectangle, you might want to fill it with a color or a texture or some sort of a pattern, right? So that's going to go into another class that's not a shared responsibility with line elements. So that's what it looks like. So this is the final version, so to speak, of the drawing editor class hierarchy. So it has the line style, and then the fill style, and then the children at the bottom. Does that example make sense? Hopefully. So we're going through an example of how to design a good class hierarchy. Notice that the concrete classes are at the bottom, and the abstract classes are higher up, and that there are no abstract classes inheriting from concrete classes. And there's no multiple inheritance either here. Abstract classes should not inherit from concrete classes. We already mentioned this as a guideline. Here it is in a little bit more detail. Abstract class behavior should be implementation independent. Right? By definition, there is no implementation of an abstract class in Java. Concrete class behavior may be implementation dependent, so depending on what object you're actually implementing or representing. If this characterization is violated, if an abstract class inherits from a concrete one, then this is something you want to avoid. So this is what we want to avoid, right? Can anybody say why this is illegal? I don't know what. This violates the principles here. Why is this illegal? Can anybody say that in its own words, or in the words of object-oriented design?
Is the class an abstract class?
Yes, it's an abstract class. That's right. That's right. You're getting warm. And any second part?
No, so I was just asking if class A is abstract.
Yes,
class.
it
So
is.
basically, it's because class C already defined all the functions, and class A we cannot take an object of that. So and class A is supposed to, like, object of class A should be supposed to take the functions that are implemented in class C.
Exactly. Does everybody have their helmet on? Nice. That's exactly right. So that's what I was. Abstract. Class A is supposed to be abstract, right? In this diagram, Class A inherits all the responsibilities of Class C, but Class C is concrete. So Class A is not allowed to have concrete responsibilities, right? Otherwise, it's a concrete class. It just doesn't make sense, right? And we can think of Class A is a kind of Class C, right? But Class C is a kind of concrete class. But Class A is supposed to be abstract. Class A can't be a kind of concrete class. So that's another way of thinking about it in this language. And you can use the natural language to help you make sense of these hierarchies. The natural language should help. So how can we fix that? We can introduce a new class called Class A2 that has abstract behavior, and then Class C and Class A can inherit from that new abstract class. Right? I think these kinds of things happen. I know why these kinds of things happen and why the is part of relationship gets confused. Nikki, did you have a question?
Well, what do you mean by concrete responsibilities?
Concrete responsibilities are methods that have an implementation. Yes, some methods don't have any implementation and they're abstract. Yes. They only, so a method that's just the name, input parameters, and the return parameters is an abstract method. It's the definition of a method, but it doesn't have to have an implementation. It just has to define. Anyway, there's another way of saying it is it just defines the communication between two objects or two classes. How they communicate with each other. That's also called a communication protocol. You can also think of it as a communication protocol, right? And then it starts to overlap with networking, right? This concept, because it does overlap, right? Client server, you use protocols to communicate between a client and a server, right? The classic example is a web browser and a web server, and you're using protocols to communicate between. Which protocol are we using? Anybody know? Which protocol are we using if we communicate between a web browser and a web server? Anyone? That's a networks. Are you taking networks? Is there a networks class in this? I don't even know if there's a networks class. Name? Oli.
HTTP.
That's right, the HTTP. The P is protocol. Ready? That's right. Okay, I just went off on a little tangent, I guess. But it's all the same. All these concepts are the same. They're all connected. Okay, and then we can eliminate classes. Classes that add no new functionality are normally eliminated. You might have had an idea for a class and it gets eliminated, or it doesn't add anything new, or it gets its responsibilities get put into another class, and it didn't end up the way you thought it would. A class can have no new responsibilities but still add functionality. So for example, an abstract class. Responsibilities represent only public services, public methods. That's public methods, so not the private methods. Right? Responsibilities are inherited by children and assigned to a parent. And if a child implements the parent responsibility in a different way, then it adds functionality. Right. Okay, little quiz. We have two hierarchies here. One on the left and one on the right. Unit, square, square, rectangle, rectangle, square, and unit, square. Which is a better hierarchy? Quiz time. Everybody can see that? Okay, so raise your hand if you think the hierarchy on the left is the better one. And raise your hand if you think the one on the right is the better one. Okay, and raise your hand if you don't know, if you just like, I'm not sure which one is the better one. Okay, anybody want to explain which one is better and why? Anybody want to justify their answer, Nikki?
So I mentioned before that we have to put more responsibilities to the upper sides. More responsibilities.
Say that sentence again.
So we said that we have to push responsibilities as up as we can.
As far up as possible. The word that I'm not sure about in that sentence is we have. You said we have to push responsibilities.
Should.
Or we can try. I would change that, we try. It does, we don't have to.
But it's better.
It's good if we can. It's good if we can. Anyway, sorry, keep going. So you said the left or the right? The right, okay.
So in the right one, the rectangle has more responsibilities than the square, and square has more responsibilities than unit square.
Okay. Yes, that
But on the
looks like
left
it's
side,
true.
the responsibilities increase as we go down. That's why the right one is better.
Okay,
Like,
okay. Did I give you a piece of candy? You didn't have to go trick-or-treating this year, you just come to this class. No pun intended. Any other opinions? Name?
Thomas.
Thomas.
Yep. Okay, I prefer the one on the right for this one reason, and that's because if you use the one on the left, and let's say you got a function that asks you for a square, you can still stuff a rectangle in there, and it will still take it, which is gonna cause problems because you're rectangle-less.
Okay, that's a good answer. I wasn't thinking of that one. Any other answers? James?
On London, so
Say that
on
again?
London,
Brendan.
yeah.
Okay.
So to inherit from another object, you have to be something of that type. So are rectangles a type of square? Well, if the rectangle is 1 by 1, sure. But a 1 by 2 rectangle obviously isn't a square, so we still need to then inherit from it. Whereas, a square is a type of rectangle, a unit square is a type of square, so it would make sense to inherit in that sense, so that's why we like to understand.
Brandon, that was the answer I was hoping for. Thank you. We can look back to natural language as a guide to help us answer this question. The is kind of relationship. If I try this with the left side, square is a kind of unit square. Okay, that's very, that's not a very clear formulation. Rectangle is a kind of square. False. I can say that clearly. Rectangle is a kind of square, it's just false. Everybody see that? If I look at the right one, rectangle or square is a kind of rectangle. Yes, that's correct. Square is a special kind of rectangle, where all 4 sides are the same length. And unit square is a kind of square. It's where every edge has unit length. So that's the correct hierarchy. Why is this confusing? This is confusing. That's why we're going through this exercise. And people get this confused all the time. All the time. And Nikki was pointing out or hinting at the confusion. We're not modeling complexity here. So we're not saying children must be more complicated than their parents. This is not the kind of relationship we're modeling or we're trying to represent. And this is very confusing for many people. They have this idea that they say, okay, child must be more complicated than parents. No, that's not true actually. The child can be much simpler than the parents. The parent could have lots of responsibilities and be very complicated, and then the child has just one little responsibility, like, I can't think of a good example off the top of my head, but the child can have very few responsibilities and the parent can have many responsibilities. There's nothing wrong with that. And a lot of people get that confused. They look at the left one and they think, okay, it goes from simple to a little bit more complicated to most complicated, therefore this is the correct one. No, that's just not what we're trying to achieve. We're not trying to build a hierarchy that says parent is the simplest, child is the second more complicated, and then the grandchild is the most complicated. That's just not the relationship we're trying to design. And that's the reason it gets complicated. The reason people get confused. I think that's the reason people get confused, based on my observation of people. Good. Any questions about that? Could be a very nice test question, couldn't it? Okay, so let's go on to the next topic, which is not hierarchies anymore. I just uploaded, by the way, the slides for collaborations and hierarchies. I didn't have time for the subsystems one yet during the break. Any questions before we start talking about subsystems? So we're going kind of quickly, but I just wanted to make sure, but I would say we're all caught up now, so we don't have to go especially quick. So let's talk about subsystems. Right, so far we've talked about identifying objects, identifying responsibilities, identifying collaborations, assigning those collaborations to responsibilities and objects, and then designing hierarchies. Right? Now we want to go to the next stage, which is identifying subsystems. So we want to, if we have a bunch of classes and a bunch of collaborations, imagine drawing edges between all those classes. Every method call is mapped to an edge in a graph. It can get complicated. Right? You can imagine a graph with just edges pointing everywhere in this crazy, crazy mess. So now we want to straighten out those edges, so to speak, and make the patterns of collaboration simpler. We don't want 1,000 classes that collaborate with that all collaborate with each other, that collaborate with the other 999 classes. We do not want this. Right? So we want to simplify the patterns of communication, simplify the design. And we do this, subsystems are a way to do this, to simplify the patterns of communication. Design good interfaces to subsystems and classes in order to simplify control and flow of information. And we're going to look at the collaboration graphs, revisit the collaboration graphs and subsystem. We're going to look at subsystem cards. Collaboration graphs represent the flow of information in a system. And I'll just remind you, this is the difficult part of object-oriented design, trying to understand the flow, the process flow, the flow of information, the flow of processes, the order in which things execute. It's really difficult in object-oriented design. Information and control flow occurs dynamically during execution. In order to understand the overall design, we need a static representation of all the paths along which information can flow. So every method call represents some flow of information. Right? The input parameters are information, the return parameters are information, and we want to understand how this information moves around. Collaboration graphs can include classes and their hierarchies, contracts, which is a set of responsibilities, and collaborations. Here's an example. A collaboration graph class representation. So here's the parent-child hierarchy diagram. we can draw that same diagram as a nested representation where the parent is the big rectangle and then the children are smaller rectangles inside the big rectangle, right? And this is more typical inside of a collaboration graph. Here's a complicated example where we're going back to multiple inheritance, and another good reason to avoid multiple inheritance is because it's very difficult to represent using this nested graph notation. Right here, we've added a border that indicates the class is expanded elsewhere, so array gets expanded somewhere else, and a double line that shows that a class has another parent. So array has two parents, right? Ordered collection and indexable collection. But here, it's how would you draw that in this nested representation? Well, it is possible, but it's not very obvious. So here it's been broken up into two rectangles, right? Ordered collection, and then indexable collection right here. And then matrix. So, and matrix also has, oh no, it doesn't have two parents. String has the two parents, right? String here. The double line shows that the class has another parent. So it's complicated. Like, try to figure that out. Imagine having this drawing and having to recreate this. It's non-trivial. It's confusing. We just mentioned contracts and collaborations. Contracts are represented by numbered knobs on edges of classes. So that is a contract. That just means it's a way of annotating collaborations. It's saying, okay, this is a description of this collaboration, and it gives it a label, right? And then we can actually document it, like collaboration number 1 or contract number 1, and actually write a description of it, right? Collaborations are arcs from the client class edge to server contract. We can simplify collaboration graphs by using information hiding, right? And decide not to display subclasses in their collaborations. And we can eliminate entire sub-hierarchies that define no new contracts. We're going to go through some examples of this so it actually makes sense. What is a subsystem? A subsystem is not the world's easiest thing to define, actually, because it doesn't exist. It's only in our imagination subsystems. They don't actually exist. A group of classes that collaborate amongst themselves to support a set of contracts or closely related responsibilities. From outside the subsystem, the classes work closely together to provide some function, some responsibility, right, to the rest of the system. From inside the subsystem, the classes have a complicated set of collaborations in class relationships. But this complexity really should be hidden from the outside world. You see this kind of idea, this hiding of complexity all the time, right? Imagine unfortunately, the only. Does everybody know what a DVD is? A DVD still being used. Everybody know what a DVD is? Does everyone know what a DVD player is? You see, like, you can imagine the DVD player as a subsystem, right? It's got a box. There's a box around that DVD player. And you don't have to know how it works to play a DVD, right? The only thing you have to know is how to insert the DVD and then press the play button. So that's the interface. You can think of that set of buttons, like the play, the pause, the stop, the rewind, forward one, as the interface to that DVD subsystem. And then the casing around the DVD subsystem hides the complexity, because it is complicated, right? To play a DVD is very complicated. Like, have fun trying to build that from scratch, right? You have to have the perfect disc, you have to have the perfect laser, it has to be spinning at the perfect speed, you know, and everything. So that's like a subsystem analogy. That interface that you see with the 5 buttons is very simple and very understandable, and it hides the complexity of what's actually happening inside the DVD player. Right? So it's like a subsystem. Superclasses are not to be confused with subsystems. A superclass groups a set of classes with identical responsibilities, right? The is kind of hierarchy. A subsystem is a group of classes with different responsibilities that work to fulfill a common purpose. So here we have the is kind of hierarchy. That's what the superclass describes. Also called a parent class to confuse you. And the subsystem is really is we're thinking about the is part of relationship now, not the is kind of relationship. Subsystems are all about composite hierarchies, not class hierarchies. I hope everybody understood that. Subsystems are not conceptually different from classes, just a matter of size and scale. Subsystem contracts represent the services provided by classes in a subsystem to classes outside the subsystem. In the DVD analogy, those 5 buttons, play, stop, forward, wind, rewind, pause, are a contract. And they represent what the DVD player can do, the DVD subsystem can do. Okay, let's look at some examples. The printer example. Here we have a class called printer, a parent class called printer. We have a child class called dot matrix and laser. These are a little bit outdated, these examples. Does anyone know what a dot matrix printer is? Anyone? Has anyone ever heard of a dot matrix printer before? Do you know what a dot matrix printer is? I have a lot of handy stuff. Does anyone know what a dot matrix printer is? It's the printer, like, it uses a ribbon, like a typewriter. Everybody knows what a typewriter is? What were you going to say?
I was going to say, is it like just a normal printer, but instead of printing everything normally, it just does everything in really thin rows of dots?
That's right. What's your name? Harry. Yes, and it prints. It uses like a dot a matrix of points to form letters, right? By connecting those points in the right shapes, and it prints on a ribbon, like a typewriter. Anyways, it's not important. And then there's a laser printer. There's another class called print server. And instead of trying to collaborate with these individual classes, we've put them all together in a subsystem represented by this outer rectangle. And we collaborate with the subsystem, not the individual classes themselves, because it gets too complicated, right? The printers are changing all the time. You know, it could be, there are a million different kinds of laser printers. There are lots of other kinds of printers, right? It could be a soft software printer, like PDF, for example. So instead of trying to figure out how to collaborate with all these different printers every time there's a new printer, we can define a subsystem called print, right, and collaborate with that subsystem. And that actually, in this example, gets assigned to the print server class, right? So subsystems are the final stage of design. Well, they're not the final stage of design, but they're getting close. The final stage is protocols, which is the next lecture. Subsystems help to simplify design near the end of the design and can be used early in the design process for a complicated application. So in this example, we were describing a bottom-up subsystem. We start with the individual classes. We start putting them together and form bigger subsystems. But you can also take a big application like the drawing editor and then identify the major subsystems first, and then the classes and objects and the subsystems. And that is a design. That's also a design pattern. You'll see many design patterns work that way, like the MVC design pattern. So it's a top-down approach to identifying classes and subsystems. A subsystem might start out as a class. If it gets gesundheit, if it gets too complicated or has too many responsibilities, it might get subdivided. This is something that if you're a software engineer, you should be thinking about all the time. This guideline gets violated so many times, like an infinite number of times in the real world. This is something that software developers are very, very poor at, generally speaking. Instead of taking a complicated class and subdividing it into simpler classes, they just keep expanding and expanding and expanding and expanding until the whole thing breaks, right? Remember we talked about that method that's 5,000 lines long, and at some point nobody can touch it ever again. Does anybody know what that's called? Source code that can never be touched again? There's a name for that. It's so popular, it has a name. Is it Brandon?
Yeah, spaghetti code.
That's not the answer I was thinking of, but I'll give you a piece of candy. Anybody know the proper term for the code that can never be touched again? Most of the code that exists in the world is this kind of code and can never be touched again. Never. Name? Roar. Roar. What is it called?
Roar.
Roar.
Yeah.
That's your name?
Yeah.
Okay. Proprietary code? That's not the word I was thinking of, but I will still. This is dangerous. Everybody put on your helmets. Oh, that was way off. This is an important phrase, actually. Name? Harry.
It's a legacy system.
Yes. Legacy code. Yes. Most of the code that exists in the world is legacy code. Yes. So, I'm looking at a slide here. It doesn't look very interesting, this slide, does it? It doesn't look very interesting, it's true. If a class gets too complex or has too many responsibility, it gets subdivided into more classes that combine into a subsystem. Usually what happens in the real world, a class gets too complex and they don't go to the next step. The developers do not go to that next step because they never took this amazing module and they don't know. And what happens? It turns into legacy code. Code that can never be touched again. right? If a method is too long, it can never be touched again because everybody's afraid of breaking it. The behavior is unpredictable. That's what happens in the real world because not enough software developers have actually taken a software design module. Right? I should put this in bold. I should have put that in bold font, that one. Subsystems are conceptual, so they don't actually exist necessarily. You don't have to instantiate a subsystem at runtime. Their classes may exist during execution, but they don't. Sometimes one of the classes in a subsystem is an interface class. So yes, if you want to actually implement and define, have a well-defined subsystem, you introduce a class that's an interface class. And all the communication goes through that interface class. And that's all that we have to know about is the interface class, and we hide the complexity of the underlying system. The interface classes may not directly fulfill their responsibilities. They just pass the message on to the relevant object inside the subsystem. The subsystem concept can lead to more general and flexible contracts, and clients can access functionality with the contract, using the contracts. You can change an interface without disrupting the inside and the outside. So if I added a button, I can add a button on the DVD player on the interface without breaking everything on the inside or breaking anything on the outside. Right? I could add a button that says something like pause for 30 seconds instead of just pause, or the volume, like I can add a volume, turn it up to 11, right? Okay, so an example would be a print subsystem that prints only PDF files, but this could be extended to include other kinds of file types, right? And we don't have to know about the complexities inside the subsystem. All we need is we need to know about that interface. So this is how we can document a subsystem with these subsystem cards. So subsystem cards have a name, like the drawing subsystem, for example. They have their set of classes, right? Drawing is a class, control point is a class, drawing element is a class, and then there's a purpose to maintain and modify the drawing. This is a list of responsibilities: display a drawing, maintain a drawing, and modify a drawing, editing. And then these are the classes that actually get those responsibilities. Here the word contract is used. I'm using contract and responsibilities interchangeably, very loosely there. And these are the classes that are responsible for actually executing those. So we may need to revise class definitions to collaborate with a subsystem rather than with an individual class. This helps maintain abstraction and flexibility. Clients are now insulated from future changes to how the subsystem carries out its contracts. So we can make changes inside the subsystem without breaking everything outside the subsystem. This is the problem with spaghetti code. I think it was Brandon that said spaghetti code. In spaghetti code, what is the characteristic there? That every class can collaborate with every other class. And it creates this incomprehensible network or pattern of communication, or lack of a pattern of communication. And therefore, a change to any object can break the rest of the system. Right? That's what we're trying to avoid. And by the way, in Java, you can think of packages when you think of subsystems. It's not exactly the same, but the idea is a package is a group of related classes, and their functionality has something in common. right? Like the file IO package, right? All the classes that handle file IO are packaged together. Or the Java FX library, right? All the special graphical functions are in the same package, for example. Guidelines for identifying subsystems. Collaboration graphs help us to identify subsystems. Look for strongly coupled classes, classes that are always communicating with each other and always depend on each other. Coupling is a measure of how much they depend on each other, right? How frequently do they communicate? Coupling can be indicated by how frequently they communicate, right? This frequency concept is not really shown in our diagrams necessarily. Also, a strong coupling may show up as a web of many collaborations, like a kind of a small, fully connected graph, and then connecting to the rest of the software with fewer collaborations. Given a set of classes that appear to be strongly coupled, do they work together for some common goal? Do they have a common purpose? Can you name the set? And in fact, you could argue this is what design patterns are. Design patterns are a set of objects and classes that are always working together and provide a solution to a common problem. We're going to talk about design patterns next week. But they have these properties. They're a set of classes and objects that fulfill a common goal or a common function. They have a common purpose, and the purpose is well known, and it's always reoccurring, and they all have a name, right? They've all been given a name. Some of the names are confusing and are hard to understand, but they all have a name. Okay, here's an example of a subsystem card. The drawing subsystem of the drawing editor to maintain and display a drawing, right? The classes in that subsystem are drawing, control point, drawing element, and the drawing element's children. And then the set of responsibilities it has to display itself, to maintain the elements in the drawing, to modify an attribute of a drawing element, test the location of a drawing element, modify the geometry of a drawing element, and these are the classes that carry out those responsibilities. This is what the subsystem graph can look like for that. So here we have the card, and here we have the graph representation of that same subsystem. This is using a notation from the book, right? There are 3 contracts here, or sets of responsibilities. Here's our drawing subsystem. These are carried out using the drawing class. This one's carried out using the control point class. And look, there's even another subsystem, or possible another subsystem here, right? The drawing element subsystem. This is that same graph drawn in UML. Right, everybody's favorite design drawing notation, UML. It's actually kind of nicer because instead of these numbers, we have the text that says what the responsibilities are. The numbers are very mysterious. Here, it's nicer with these. What I find confusing about this drawing, though, is it has these patterns of collaboration. For example, drawing collaborates with drawing elements, but then it has hierarchy graphs in the same picture. I personally find that confusing. Okay, I think maybe we should stop. What do you guys think? I think everybody looks worn out. So I think, yeah. Anyway, there's a preview of the other slides. Any questions? Any questions about anything? Okay, we'll stop for today. And happy Halloween, even though it's just a few days ago.